Welcome, everyone. Last year's conference on robot learning, or CORAL, was the largest in its history with over 900 attendees, 11 workshops, and nearly 200 accepted papers. There were numerous groundbreaking ideas, but one debate took center stage. Can training a large neural network on an immense dataset solve the challenges in robotics? This question has lingered for a while, but gained renewed importance after the success of large-scale models like ChatGPT. Developing a general-purpose robot capable of performing a wide variety of tasks is a long-standing goal in robotics. With recent advancements, it seems plausible that scaling existing network architectures on large datasets might be the key. The aim of this discussion is to present the different sides of this debate, as heard during CORAL without bias. Let's start with the arguments supporting scaling as a solution for robotics. Firstly, it worked for computer vision and natural language processing, so why not robotics? Training large models on vast amounts of data has brought significant advancements in these fields, with models performing tasks they weren't explicitly trained for. Advocates like Chelsea Finn and Russ Tedrake highlight the promising generalization capabilities seen in recent studies, suggesting similar success could be possible in robotics. Secondly, progress in data, compute, and foundation models are trends we should harness. Rich Sutton's influential essay notes that simple algorithms that scale well with data outperform more complex ones that don't. This suggests that riding the wave of improvements in data and compute could be crucial for robotics success. Also, large models might help us discover the simpler manifold of practical robotics tasks within the complex space of all conceivable tasks. By training on large datasets, we might uncover a more manageable subset of tasks, leading to unexpectedly competent generalist robots. Lastly, large models are thought to bring common-sense capabilities to robotics. Many subtle nuances in robotics tasks, like placing a mug on a table without spilling its contents, require common-sense reasoning. Large models trained on extensive data might bestow these essential abilities. While these points are compelling, let's also consider the arguments against scaling as a practical solution. A significant challenge is the lack of extensive robotics data. Unlike CV and NLP, the internet isn't brimming with robotics data, making large-scale data collection costly and difficult. Additionally, the diversity in robot embodiments and the environments they operate in adds complexity to creating a comprehensive data set. Another concern is the cost and energy required to train such large models. For instance, training GPT-4V was immensely expensive and energy-intensive, and scaling this up for robotics might be impractical for most organizations. Even if large models work as well in robotics as they do in CV and NLP, they might not achieve the 99% reliability required for practical tasks. Current models, even in their fields, don't reach this threshold, highlighting a fundamental challenge that scaling alone might not overcome. Experts argue that combining classical approaches with new learning-based methods might offer the best short-term solutions. This hybrid approach leverages the strengths of both techniques, as shown by successful real-world deployments like those in Boston Dynamics and Texas hospitals. Taking all these into account, here are some key takeaways. Firstly, scaling up learning with very large datasets is a promising direction and merits further investigation. This approach could unlock significant advancements and insights, even if it doesn't wholly solve robotics. Secondly, we should continue exploring other existing methods. Classical techniques have a proven track record, and their integration with learning approaches could yield reliable solutions. Furthermore, focusing on real-world mobile manipulation and user-friendly systems can prevent the community from getting stuck in less generalizable local minima. Lastly, transparency in reporting negative results can save repeated efforts and offer new insights, and thinking outside the box might lead to novel approaches beyond the current paradigms. Thank you for joining me in this deep dive into the ongoing debate in the world of robot learning. Until next time, stay curious and keep exploring.